I'm now going to model how a nerve impulse is initiated, transmitted, and the result of that transmission on a second adjacent neuron. This is a great lesson to teach because you can lead students into the discovery of, nicotinic receptors. Nicotine is a drug, and you can then go into drugs like cocaine. After this, I teach a really interesting lesson on, how does somebody actually get physically addicted to cocaine, and, actually show them the protein channels, changing numbers and all that stuff. So what I built here is one large neuron. So this is the cell body. Here's the initial segment, and we have our first sodium voltage dependent channel and a second sodium voltage dependent channel. You can clearly see how I made the axon split into two, in this case, axon terminals. Here's our neurotransmitters. Calcium's in the synapse, calcium voltage dependent channel, and this is a receptor that's going to receive the neurotransmitter. So basically what I do is I put a few electrons in here and some proteins to communicate to the students that this cell body at resting membrane potential has a particular charge because of the ions and the proteins, and we all know what those numbers are. And we call that resting membrane potential. Now, when I bring sodium into this environment, I'll tell the students, don't worry about why or how it got in there. We're going to learn that in a minute. But they can all clearly understand that if the charge in here is negative, whatever the number is, right? In this case, 70. If we bring positive ions in, we're moving closer to zero. And that's how I establish, by bringing sodium in, we can get to that magic threshold of minus 55. And I've spent a lot of time before this lesson talking to them about protein shape and what can change that, with heat and pH and other proteins and, phosphates. And in this case, I'm trying to communicate to them, here's another example of a particular charge now, minus 55, affects the shape of these proteins, and the sodium voltage channels, they are dependent upon that charge. And that's how I communicate sodium now entering. And you can see here in this model, I'm bringing in twice as much. That's representing a nerve impulse of plus 30. And I'm clearly showing the students now that this is not happening. That this charge is so strong, right, that it can open the adjacent channel, right, and now sodium will enter. And this charge is so strong, it's now going to open the calcium channels. Calcium will enter, and you can teach whatever type of detail you want regards to reactions with calcium. Fact of the matter is, a set of reactions happen, the neurotransmitter is released into the synapse. The neurotransmitter binds to the neurotransmitter receptor. Now at this point, we'll bring in our sodium neurotransmitter dependent channel. We'll place some sodium in the synapse. And now I'm going to build a little cascade of proteins here. To demonstrate the relationship between the neurotransmitter and this sodium neurotransmitter dependent channel. So now it's not a charge, it's chemistry that changes the shape of this protein, and that shape change allows for the adjacent neurotransmitter to open. Sodium enters the cell body, and now we can reach threshold, and this can continue. Now we have to bring this neuron back to resting membrane potential. So you can see in your model that I need to build a sodium potassium pump. So I need one more protein. we have large amounts of sodium that need to be pumped out. And you know, I'm just clearly going to demonstrate, as you all know, that 1, 2, 3 sodium can get pumped out, 2 potassium can get pumped in. I spend a little bit of time talking about the actual volume of ATP used daily to drive this, which is around 33% of the total amount. And this extra potassium needs to be pumped out. If it does, we have our potassium voltage channels. And those potassium voltage channels, if the charge here is too high, can open. And again, remove those positive ions, whatever the volume is, to go back to resting membrane potential. So that's how I model a nerve impulse, and that leads into what I mentioned about drugs the next couple of days and the history of actually finding neurotransmitters. So I spend about 4 or 5 days on this in total. And that concludes my demonstration on a nerve impulse.